50 years old, secondary 3 for NS High School. In this lesson, we'll be continuing with physical chemistry, the hydrogen spectral series. Alright, so for previous few lessons, we were taking a look at the Rydberg's empirical formula. Empirical formula. That means Rydberg, at first when he discovered it, it is through a series of experiments. So by the results, he concluded that he has this formula, and in fact it is quite accurate, since in the previous lessons we have already shown how you can theoretically derive the Rydberg's empirical formula by combining two of the laws in classic physics, which you have the Coulomb's law and the Newton's second law. Now beware, this is only for hydrogen, so that means for the Coulomb's law you just have one positive charge and one negative charge. Or for your Newton's second law, you have to be aware of the circular motion. Alright, so by combining the two, you get an R. And with this R, at first you couldn't find what R is, since you have your V. So then you could move on to your modern physics. Well, in modern physics, you start by using quantization of angular momentum, which is your Bohr's assumption. So over here, Bohr, he combined angular momentum with his own kind of, assumption. So he gets this kind of a thing. Then you just make a substitution to get R. And at last, this R over here is what you call the Bohr's radius for a hydrogen atom, which, if you know the radius of a hydrogen atom, or should I say the diameter of a hydrogen atom, which is 1 angstrom. So it is 1 angstrom is around 1 times 10 to the power negative 10, right? So that means radius, it'll just be that halved. But for specific or more exact values, you could try to calculate this on your own, since basically all of these are constants. But of course you have one thing to take note of, M. What is it for? It is for electron. E, this is not your logarithm. In fact, this E is the amount of charge on your electron. Then of course N, since it's just a hydrogen atom and it is in its ground state, that means N, you just take it as a 1. Alright? So after you get this Bohr's radius for hydrogen atom, you move on to someone pretty much everyone knows, especially when you start learning. This might be one of the first scientists you hear of or know, which is Einstein. So Einstein used the Planck-Einstein relation, which is down here, to derive a different set of things, which you can find this part and do some calculations to get finally your Rydberg's empirical formula. So what's so special about all of this? And of course, there is one main problem. If you can recall what was up here, which is your mechanical energy, you might be wondering, wait, how do you get the formula for your potential energy? Alright? So this potential energy part is actually one big problem, which we will be showing it later in this lesson. So those are some of the main things that you will have to take note of. Alright. So let's start what we would need to start in this lesson. First of all, we could take another look at F equals ma. What's so special about F equals ma? Since you have a linear form and you have your counterpart, so what's so special about that? Now F equals ma, and if you can recall what the other was, you used moment, right? So when you use moment, that means you will have I beta. So these are the two things that you are looking at. Alright, so for A, this is a second derivative of, so what can you use over here? So it is a first derivative of your speed, velocity, which is your v. So second derivative, it depends on how you would like to write it. Of course, you could have stuff like d or s or whatever you like to use, alright? So let's just say s for distance. It just depends on what you like to use. So a second derivative. Alright, so then beta, which is your angular acceleration. So this would have your second derivative theta with respect to t, right? So here, one is linear acceleration, the other is angular acceleration. Right, so what's so special about all of these? Well, of course, these are one of the differences between the two. And with your different types of acceleration, that means you have to be aware of in which case are you looking at which type of acceleration. So if you have linear acceleration, which then you will have your force being your mass multiplied by linear acceleration. Whereas if, let's say, it is spinning in circles, which if you're finding the moment of it, you could use your moment of inertia multiplied by angular acceleration. So these two, they look pretty similar. What they mean looks pretty similar, but of course you have to be aware they're not the same. So how about another form of these two that they can look pretty similar but are not the same? So another form is, let's say you represent F as delta P delta T. So what is P over here? It is not power, but it is momentum. So F is your change in momentum over change in time. So how about you represent your moment in a similar form? So is there a similar form? Yes, there is, which is M is delta L over delta T. Well, of course, you could also use like dP dt, which they pretty much have similar meanings. It's just that d would be infinitesimal, alright? So you have these two parts which they look pretty similar. So P is your linear momentum. Then what is L? L is angular momentum, alright? So again, these two, they look pretty similar but are not the same. Now, is there any other form which you can represent them as? So how about let's take a look at, now we have differentiation. What is another, the counterpart, should I say, of differentiation? Which of course is integration. Now, what can you represent this with integration? So integration, let's just say, in this part behind it is a dv. So what do you think I put in front here? Well, pretty much all the time, you could just say it is a rho. Beware, this is a rho and not a p. So what is so special about rho? Rho here is your density. But density of what? So if, let's say, you want to find the F, or you want to find M. So if you want to find the M, rho will just be your mass density, which is your mass divided by volume. Alright? So that is what you could represent M as. Well, for the other part, which is your moment of inertia, also known as I, so how can you represent that? Also with integration. So for your moment of inertia, now how is it different from your normal mass? So if you can recall how to calculate your moment of inertia, you have mr square. So you would have rho and then an r square. Alright. So these are the main things that you could be taking a look at. So wait, now if you think more about these two forms, are there any other things you can think of? So let's say your increase in, so let's say you have basically no force. Now what does that mean if you have basically no force? Could the time difference approach infinity? It doesn't seem likely, right? So that means your change in momentum has got to be 0. So this part, when you have no force and you change your momentum, then your change in momentum is 0. While for the other part, if you don't have your moment, then your change in angular momentum is 0. Now if you think about it, is there any other way to describe it? So that means if you can think of it quickly enough, then you will notice that for the first part, you could call it momentum conservation. Alright, so if f is 0, then delta p is 0, and that means you would have a momentum conservation of your system. Alright, so how about for this part over here? Now if here is momentum conservation, what is the other? So the other, well, might be pretty obvious after you know the first, would be angular momentum conservation. Alright, so now that we have covered these two, did you know that there are a few other types of conservation that you would normally have or have to learn? So these are just two types of conservations that you could learn. Well, the other two which you have, they could be, so these are different, they are not the same anymore. One of which is mechanical energy conservation. Alright, so this is just one of the other types of conservations. While for the last part, it won't be that much of a conservation anymore, since if you want to talk about main things that build up physics, the physics that you are learning currently, which would have your work energy principle. Alright, but for this part we'll explain more in the future, alright? So now that you know all these four, and we have kind of looked into momentum conservation and angular momentum conservation, which when your force or your moment is 0, that means your change in momentum or change in angular momentum is 0. Now let's take a look at mechanical energy conservation. Did we use it anywhere earlier in these lessons? So if you recall, we did have one part about mechanical energy, which your mechanical energy is equal to potential energy add on to your kinetic energy. And for that part, it is more of just calculating your mechanical energy at that point of time, or should I say, now let's just take a look at it. So it's just an E2 minus E1, which you have your Planck's constant. Well, you could write it as this, or HF, or HC over lambda. So these two are just the mechanical energy that you actually calculated, which isn't too much regarding your conservation, alright? But since your mechanical energy within the system, whether you have potential energy or kinetic energy, no matter what you do, the total amount would still be the same. But for this part, it is finding the change in the energy that you have. But then you might be wondering, isn't there a conservation? Well, you have to think about it in other ways, like how can energy be lost to other places, right? So you can think about it like that. And then you might find out why there would be the difference in the energy between, let's say, this is the first shell, this is the second shell, and the third, alright? So of course these differences should be way bigger, since if you have learned about how to find your radiuses, they actually pretty much expand quite a lot. So then you will have, let's say, first shell and second shell, which you do have. Now how can you change this? You have Hc Rydberg's constant. Beware, this is still for hydrogen. Of course, you can have stuff like helium where you have two different electrons and then you have to calculate other things. But for this case, we're just looking at hydrogen. And then 1 over n1 square minus 1 over n2 square. Alright, so we have something like this. Now, on the first one, if you realize, n1 is pretty much always, now, since you have to have this part as positive, that means the denominator of the first fraction has to be smaller than the denominator of the second fraction. So n1 is always smaller than n2, but other than that, they could be any integer, alright? So they can be any integer with the condition that n1 is smaller than n2. I mean, if it is equal, then they're just zero, since if an electron on one shell stays the same, there will be no energy lost or gained. So if we take a look at this, that means from the first shell, you want to go to the second shell. So that means you would have to take in energy. This electron has to take in energy in order to get from the first shell to the second shell. And that energy is calculated by the energy needed for your second shell minus your energy needed for your first shell, right? So that's pretty much for this part, if you can get it. Of course, we could explain in more detail in the future lessons, alright? So that is pretty much the basics of what you will see for this part here. Alright, now for the question that probably most of you are wondering, since you have mechanical energy, that is potential energy plus kinetic energy. Now kinetic energy, half mv squared, everyone will be familiar with it, which you would probably know why you can calculate kinetic energy that way. But your potential energy is your main problem, since most of you will only learn gravitational potential energy. But you have to realize there are other types of potential energy, whether it is that so-called chemical potential energy set by your teachers, which is actually completely irrelevant here, or in this case, it is actually electrostatic potential energy. Okay, wait, it sounds confusing. Now you have more types of potential energy. So how exactly is this calculated? Right, so let's think about it first. MGH. What is so special about MGH? If you only have mg, which is your weight, now if you multiply that by, let's say, the difference in your height, then you will have your potential energy. So how about let's think about it in terms of electrostatic things. Electrostatic field. So let's say this is your positive charge, your proton, your nucleus or your core, and you have one electron here, E, alright? And the distance between these two initially is R. And you can have this E pushed a long distance to, let's say, infinity. Alright? So, when you think about this, it is kind of like MGH, isn't it? You have your force and you have the distance that it is pushed away. So, of course, you can think of it as being pushed, this E being pushed all the way to infinity, but just to avoid more confusion, I will just remove these arrows. So I hope this makes it less confusing, alright? So now it is only the E moving towards infinite distance, alright? So you had an F, which is your Coulomb's force, you had an E, which is your electrostatic field strength, and now this case we would be calling it U, alright? So for U, what you would be seeing is integrate from R to infinity, -1 over 4 pi epsilon naught. So Q1, Q2 is just a proton and an electron, which in this case it is E squared, and R squared dr. Okay, so this might be what you have been taught. But what if you want to expand this a little bit more before you reach this step? Then for that, you will have to involve something called your dot product, which some of you might have learned. Well, for dot product, alright, so for this part, then you might be wondering, why is there a negative sign in front, right? Since if some of you can recall, when you have your electrostatic force, it is just 1 over 4 pi epsilon naught. Then of course you have Q1, Q2, and over R squared. But since this is a vector, this side also must be a vector. So the three ways to represent it are unit vector, the other way of writing R unit vector, and of course just using R vector. And then each of these, you can use either one, then you have to use dot product with the R vector, which since they're in the same direction, and that means it's just multiply the magnitude with a cosine 0. Cosine 0 is 1, so this is what you would have. Now, back to this problem of negative. So, since you have a positive and a negative charge, and here it is Q1 and Q2, so that means you have a positive E and a negative E, which would give you this negative in front here. But then again, you might want to explain more context, right? Since what is doing work done on this E? Since by right, the positive charge, or the proton and the electron, is supposed to attract, but it seems like that they're moving further away from each other. So what exactly is going on? That means there is an external force acting on this E over here, alright? So the external force acting on the E, that makes it go further away from your proton, right? So now, when you think about it again, so what if there is that external force? Now, since the external force is doing work done, that means the energy of your system would actually increase. But what has that got to do with this part? So if you think about it once again, from R the position at R to the position at infinity. And since this is a negative sign, well, it's actually pointing towards that way. Since a negative, if it is a positive, it would be in the same direction as your R, alright? So negative, that means it just points in the other direction. And since it is in the other direction, later on you would realize, let's say we have a UR and a U infinity, then you can determine, or you can already know whether it is the so-called increase or decrease, alright? So since I've already said it's an increase or decrease, that means you can also write this as delta U, but it's up to you. Get it? Alright. So from this part, when you want to integrate, this should be a pretty simple integration, since most of these parts are just constants that you can take out. Alright, so this is just r to the power negative 2, which you would see just over r now. But you have to substitute r and infinity. Now if you have something over infinity, that will be a 0. That means you have negative e squared over 4 pi epsilon naught r. So this is what you see. But what is so special about this? So since I already said it is in the other direction, that means in the other direction, it would be u e u r, or small r, depends on whatever you like to use. So u r minus u infinity. Now if you think about that, would that be an increase or a decrease? So since this is an initial minus your final, that means it is actually a decrease, alright? But then when you have u infinity, which is all the way like, it seems like it's completely different now. They have nothing related anymore. So that means u infinity would actually be a 0, since they're so far away that they basically do not affect each other at all anymore. So that means u r is actually equal to negative e squared over 4 pi epsilon naught r. And then you might question it again. Is it really possible that this potential energy is a negative? It seems weird, right? But if you only think about this, it's actually pretty correct. Since you have an external energy doing work done on your E, it gives it the energy. But since it gives it the energy increases until it reaches 0. So that means at first it would have started with negative amount of energy, which seems right. Of course, if you're not convinced, you can take it from other perspectives. Let's say, well, what if you do not take account of your external force and it is just directly work done off by your proton, alright? So then you wouldn't really have negatives and all. You can really adjust it in whatever understanding you like to take it as, but the results should all be the same. But then again, what's so special about this potential energy part? So this potential energy would explain why you could use your electrostatic potential energy for your calculation of the mechanical energy. Do you see the similarity now? What's so special about this part then? Well, if you realize okay, let's start with F. F is 1 over 4 pi epsilon naught Q1, Q2, alternatively, capital Q, small q, over r squared. And of course, this part, you can also write it as K. So this is your electrostatic force or Coulomb's force. But if you want to write a vector, then you would have or unit vector or something like that. You could also choose to remove it. It all depends on what kind of question you're solving and preferences. Alright, whether you prefer to solve it as a vector or solve it as a scalar, and different methods that can be involved. So this is your Coulomb's force. I'm sorry, there should be no more R. So this is your Coulomb's force. Then if you take a look at your electrostatic field strength, that means you have 1 over 4 pi epsilon naught. But this time it's just a Q over R square. So what happened over here? At this part, you did you remove your test charge? Well, you wouldn't really say removed, since it is actually still there, but you just divided it to make it per unit charge, which most of the time you just take it as 1 coulomb, unless they state otherwise, like let's say the unit for this is like millicoulombs or something. It depends, but generally you would just have coulombs. Alright, so next is your potential energy. Potential energy, which is 1 over 4 pi epsilon naught, capital Q, small q, over R, which is what you see over here. Now, if you're wondering about this negative again, you have to really be aware of one positive and one negative. So if you think about it again, it's actually just a capital Q and a small q. Of course, capital Q, we think of it as the capital Q exerts the force on the small q, since in this case, the capital Q, your source charge, has a lot more mass than your test charge, alright? So, other than your potential energy, the other parts that you would have, or if you could recall from lessons quite some time back, and this would actually be your potential. So potential is 1 over 4 pi epsilon naught, capital Q over R. This part we'll explain more in the future and more detailed, like let's say usages of everything, alright? But you could kind of see similarities between them, right? All of them have your K, Coulomb's constant, your source charge, but only for your Coulomb's force and potential energy, you would have an extra test charge, or your test charge can change. So for E and V, it is pretty much the similar differences, which you just have your source charge, but your test charge, you just take it as the units of charge that is given, normally 1 coulomb. Then F and E, they both have the denominator as R square, while U and V, they both have the denominators as R, which you could see why from these steps above, alright? So with these, F and U using 2 charges, 1 source charge, 1 test charge, while E and V, technically also a source charge and a test charge, but the test charge will just be taken as 1 coulomb. Alright, so these are pretty much the 4 formulas, formulae, that you would need to solve many of your electrostatic problems, or even using it in other places, like let's say what we did for your mechanical energy, which you used electrostatic potential energy instead of your normal gravitational potential energy. It really depends on the context of the question and when you can use different things. Alright, but I hope for this lesson you'll cover everything so far. I will end it here, and thank you for your watching.